today. Today's speaker is George Szpiro from the Zurich newspaper. I don't know how to pronounce it in German, who is also a great, very prolific scientific writer on mathematics, economics, and paradoxes. We'll talk today about risky decisions, how mathematical paradoxes and other conundrums have shaped economic science. Feel, as usual, please mute yourself unless you have a question. Feel free to interrupt with questions anytime, then unmute yourself and mute yourself back. Also, since we are running late 3 minutes, the talk will end in 5:53, the formal part. And then we'll stop recording, and then anybody who wishes can stay and ask informal questions and all that chat. Thank you. Go ahead, George.
Okay, hi. So I want to tell you how economics developed, and it'll be in 3 parts. The first part is about the early 18th century. Then it was just a simple puzzle about a lottery. Then up to the mid 20th century, decision-making was dominated by mathematics. Mathematics is the queen of the sciences, and it dealt mainly with how ideal decision-makers should behave. That's called normative economics. And the third part of my talk will be about the developments in the late 20th and 21st century, where you mathematicians may be a bit disappointed, but that's the end of mathematics and psychology starts entering. So I entitled that part, Man is the Measure of All Things. That deals with how human decision makers actually do behave. That's positive economics. So puzzle about the lottery. Hello. Let's say here, I'm sorry, you see the full slide always in one go. No, I wanted to do it step by step. Sorry, anyway, let's say there's a lottery where I flip a coin. If it comes up heads, you get $1. If it comes up tails, you flip it again. If it comes up, then you get $2. And every time it comes up tails, the prize doubles. So you get, do you see my cursor? No, you don't. Okay.
Yes, so we do.
Okay. So the prize becomes $8, $16, $32. The potential prize doubles every time. So how much, let's say if it's 8 times tails and then heads, the price is $128. How much would you pay to enter the game? So have a think.
You have to pay me to enter the game.
Okay, let's see. Think about how much you would pay. $5, $1. You have to pay Doron to enter the game. Would you pay $100? Well, let's see. The expected prize is the sum of the probabilities multiplied by the potential prizes. The probability is 1/2, 1/4, 1/8, depending how many times you throw the coin. And the prize is 1, 2, 4, 8, 16, etc. And that, when you multiply it out, you get 1/2, 1/2, 1/2, etc. It adds up to an infinite amount of money, actually. So why is nobody...
Assuming that you live an infinite amount of time, which is wrong.
Yes, of course. There are many reasons. Also, I'd go bankrupt if it comes up 100 times tails. But anyway, even let's say $50, hardly anybody is willing to pay $50. Why is that? Well, people always prefer more of a good than less of it. 2 cookies are better than 1, 3 cookies are better than 2. But the more one has of something, the less one wants an additional unit. So the 7th cookie, you don't really want it anymore. It adds very little pleasure. So the same thing for money. A beggar, the first dollar would mean a meal, and it's very important to him. For a billionaire, an additional dollar doesn't really mean anything. He hardly notices it. So Daniel Bernoulli in the 18th century, he wrote a paper about that, and he gave the following solution. What utility does an additional dollar give to a person? And he says utility is grows like the logarithmic function of wealth. So here you see $1 for a poor person gives a lot of additional utility, but $1 for a rich person gives only very little additional utility. So that's the square root. And his contemporary Gabriel Kramer said the square, Bernoulli suggested the logarithmic, Kramer suggested the square root. But in any case, they say utility of additional wealth always increases, but at a lesser degree. So when you do it, what's the expected utility? It's the sum of the probabilities multiplied by the square root of the expected prices, or the logarithmic, but let's say the square root. And here I compute that. It comes to the expected utility is 1.72. And since we use the square root function, that corresponds to just about $3. And that's reasonable. Maybe $3 would be willing to pay to enter that gamble, even though the expected wealth, the expected prize is an infinite amount of dollars. But we'd be willing, if we have this square root utility function, we'd be willing to spend about $3. So here comes now, that's a bit the most complicated slide. Let's say there's a 50-50 chance of either getting $2,000 or $3,000. So that's A and D. The expected value is $2,500. That's J. But the utility of $2,000 is 7.6. I'm using the logarithmic here. And the expected utility of 3,000 is 8. Now, the utility of $3,000 is 8. The expected utility of these two is 7.8. Now, what dollar amount does 7.8 correspond to? So we go to the utility curve, and then we go down, and we see it's $2,440. So that means we actually prefer, given that we have this logarithmic utility curve, we prefer $2,440 for sure to a 50-50 chance of getting 2,000 or 3,000. And the difference between 2,440 for sure and 2,500 expected, that's $60, that's the insurance premium we are willing to pay. So you see here, the $60 is the distance between H on the logarithmic curve and K, that's the straight line up from 2,500. That's the risk premium we would be willing to pay in order to avoid the gamble of 2,000, a 50-50 chance of 2,000 and 3,000. And now so we see if the curve is the utility curve is curved this way, concave to the origin, that means people are averse to risk because they're always willing to pay a premium, these $60, to avoid the risk. Now, that was the lottery. Now let's get to mathematics. How do ideal decision makers, how should they behave? And here we have Oscar Morgenstern and John von Neumann. They wrote one of the most important books in science, The Theory of Games and Economic Behavior, in 1944. Before John von Neumann and Oscar Morgenstern, Expected utility was just the solution to a puzzle. But these two, Neumann and Morgenstern, they put the whole theory on a sound footing, and they created game theory. They say that rational individuals, given 4 axioms, will choose one gamble over another if and only if the expected utility of one exceeds the expected utility of the other. And the 4 axioms are completeness, transitivity, continuity, and independence of irrelevant alternatives. So let me just go through these 4 axioms very quickly. Completeness, you always must be able to decide. Either A is greater or equal to B, or B is greater or equal to A. Transitivity, if you prefer A to B, I should have said prefer A to B, not greater. If you prefer A to B and you prefer B to C, then you should also prefer A to C. Continuity, I'll leave out for the moment. It just shows that the utility function is continuous. Independence of irrelevant alternatives, that's an important one. If you prefer A to B, and then you take a linear combination of some C, something else, and a linear combination of A to C, you should still prefer it to the same combination with B to C. So C, if you add just a bit of C to both gambles, then this C is irrelevant. You should still prefer A to B. And the main theorem is if people subscribe to and act according to the 4 axioms, game theory should guide their behavior in risky situations. But now let's say, do you have insurance for your car, your house, health? And most of you would probably say yes. But did you ever gamble? Lottery, sports, in a casino? Many of you would probably also say yes. Now, the real question is, have you ever done both? And that's strange because insurance means you avoid risk and gamble means you actually seek risk. So many people,
gambling is entertainment budget, it's not.
Yes, yes. But a rational person shouldn't be entertained. He or she should just go according to maximize utility. So many people are willing to pay an insurance premium to avoid risk and simultaneously pay a casino premium to assume risk. The casino premium, you always know in the long run the casino wins. So yes, entertainment and an adrenaline push makes you do that, but is it rational? And according to game theory, well, does that invalidate game theory? It seems irrational, but no. The short answer is no, it doesn't invalidate game theory. The long answer is, let's say a person who has $150,000 and needs another 100,000 to buy a house, will be risk seeking. He or she may enter a gamble between 150,000 and 200,000 just to get above this threshold, which allows to buy a house. So you can be risk averse until 150,000, risk seeking between 150 and 250,000, and then you buy insurance again. Once you have the house, you'll buy insurance again because you're again risk averse. So it doesn't invalidate game theory, even though it seems paradoxical. So game theory is still valid, and this gambling insurance paradox was solved by Milton Friedman, Jimmy Savage, and Harry Markowitz. They got their Nobel Prizes for more than just solving that riddle. But anyway, that's what they did. So does math guide human behavior? Game theory is based on 4 axioms. If you violate just one of these axioms, then game theory actually shouldn't be guiding you. or may not guide you if you violate one of these axioms. And which axiom is the one that people very often violate? It's the independence of irrelevant alternatives. Let's have a look. Independence of irrelevant alternatives seems very reasonable, but it's very problematic. Let's say George Bush and Al Gore in 2000 were very close. And Ralph Nader, who was a third candidate, nobody really cared about him. He was a Green candidate, but he gave the election to George Bush. Now, if he had not participated in the elections, he was the Green candidate. And we all know how much Al Gore cares about the environment. So most Ralph Nader voters would have voted for Al Gore. But since he entered the election, it actually changed the election outcome. So decisions should be made independently of this irrelevant alternative, but they aren't. Ralph Nader was totally irrelevant. And let me tell you a small anecdote about a philosopher, Sidney Morgenbesser, at Columbia. He was once in a restaurant, that's the anecdote that is being told. And for dessert, the waiter said, there's ice cream and brownie. And Morgenbesser said, okay, I'll take the ice cream. And then after a few minutes, the waiter comes back and says, excuse me, we also have tiramisu. And Morgenbesser says, oh, in that case, I'll take the brownie. So that seems totally wrong. I mean, the tiramisu was irrelevant, but it changed, he showed that it wasn't irrelevant, it changed his preference. So the big criticism on game theory started with Maurice Allais, and French, as you can see from his name. And it was, he called it École Française, the French school versus the American school. And he came up with a very interesting, here I should have really showed everything separately, but let's say, just look for the moment at the first case. Don't look at the second case for the moment. You can get either $1 million for sure, or a 10% chance of getting 5 million, 89% chance of getting 1 million, and 1% chance of getting nothing. So if you think about it, most people would probably prefer A to B. You prefer 1 million for sure and give up the 5 million because the one chance of getting nothing would really make you very angry. Now look at another case. 11 chance of getting 1 million, 89% chance of getting nothing, or 10% chance of getting 5 million, 90% chance of getting nothing. And here most people would prefer D, because they say 11% chance of getting 1 million versus 10% chance of getting 5 million. Okay, so 89 and 90 of getting nothing, I don't really care about that, but the 5 million really makes me want D. So let's look at these two cases again. First case, most people prefer A over B. Second case, most people prefer D over C. But now look just at the left now. 1 million for sure is the same as 11% chance of getting 1 million and plus 89% chance of getting 1 million. And now look at the right side. 10% chance of getting 5 million is the same as, 90% chance of getting nothing is the same as 89% chance of getting nothing and another 1% chance of getting nothing. And now look what happens. The 89% chance of getting 1 million is irrelevant in the first case. The 89% chance of getting nothing is irrelevant in the second case. And now we have the first case and the second case are identical. Nevertheless, many people prefer A, and in the second case, they prefer D. So adding 89% of getting 1 million makes you prefer A. 89% of getting nothing makes you prefer D, even though these two cases are exactly identical. And that's what Maurice Allais came up with. Oops, sorry, so people do not ignore the irrelevant alternative. 89% chance of getting 1 million was irrelevant and you preferred A. 89% chance of getting nothing was irrelevant because it happened in both cases, but you changed your preference. That was Maurice Allais. There's another paradox which is the same as Allais' paradox, but with urns, colored marbles. And I added because Ellsberg, Daniel Ellsberg is a very well-known person for a totally different reason. He published the Pentagon Papers, if you remember. And the Ellsberg Paradox is also, you can show that people do not ignore irrelevant alternatives. So now math has come to an end. We need something else. How do people actually behave? We saw game theory showed how people should behave, but apparently they don't. They don't ignore irrelevant alternatives. So now we're going to talk about how people actually behave. And the first one to do that was Herbert Simon, who got the Nobel Prize in 1978. He said that Homo economicus, that's sort of a term economists use to say a rational man, people who follow all the axioms and act according to game theory. But Homo economicus would have to be an economic superman because he needs to know his environment. He needs to have a well-organized system of preferences. Sometimes you don't even know exactly what you prefer. He must be very skilled in computation, have an ability to ignore irrelevant alternatives. We already saw that's not the case, and many more skills. For instance, let's say call options. Call options should have the price according to this formula. But a rational trader could never compute that price. I mean, logarithm of the striking price divided by the current price, and that's the variance of the stock, the underlying stock. One doesn't even know the variance. It can just be estimated based on history and the square root of the time when you're going, when it matures minus the time today. I mean, that can't be done. Nobody can compute that. But according to game theory, everybody should if you're rational. If you're rational, you pay that price. It so happens that options have been traded since the 1600s, and they didn't know what the correct price is, but they got fairly close to it because of their gut feelings, supply and demand, and so on. So there was some call price, a price for the call options, but nobody could compute that. So rational behavior must be replaced with behavior that is compatible with limitations, human limitations, access to information, collection of data, processing of information, computational abilities, ability to deliberate all facts. So that's one path-breaking paper that Hermann Simon wrote. By the way, don't get me wrong, all the people I mentioned today were first-class mathematicians. It's not that they weren't mathematicians, only in addition, they were sociologists and psychologists. So what do? We often use
but nowadays we have supercomputers So now we can ask the computers to help us make decisions.
Yes, yes. There are computers even that compute the. Let me go back to that computer. You just put in all the variables and you get the call. The price for the call option. However, you do not know the variance, the true variance of the underlying share. It's not known. You just have historical data. It can change in the future. So you have to estimate it. So not only do you need a computer, you need also historical data. And then you assume that the historical data sort of gives you the future variance, standard deviation. So, okay, computers help us, but where was I? They're not everything. So what we use, what decision makers do in day-to-day life, they use shortcuts. Let me give you a small example. An annual growth of 10% is followed by growth of 40%. The correct growth factor is 1.54. Many people would just add 10% and 40% and say the growth factor is 1.5, which is nearly okay. For many day-to-day decisions, 1.5 is perfectly fine. And you didn't spend a lot of brain power to multiply in your head. You could just add two numbers. So that's just an example of a shortcut. But there are many shortcuts. So Herbert Simon came up with the term bounded rationality. We are rational, but boundedly so. So what we should do is we don't optimize, we usually satisfy. We set a target and stop when it's reached. We don't try to maximize. We use rules of thumb. We don't use higher mathematics. So the options traders in the 17th century, they used gut feeling. They didn't use higher mathematics. So bounded rationality is not irrationality. It's just when you include the costs of the search, of data collecting, information processing, deliberation of all the facts, it's quite rational to use shortcuts, because there's a trade-off between the search for the optimum and the cost of deliberation. So you use heuristics. Heuristics are rules of thumb, like 1.1 times 1.5. So you just add 10% and 40%. Rules of thumb are based on common sense and educated guesses, and they are based on learning, experience, interaction, and feedback. What heuristics do humans use? You use usually information that you have, if it's pertinent or immaterial. You round low probabilities to 0, high probabilities to 100%. You have your prejudices and you tend to believe evidence that confirms your prejudice. You exaggerate the importance of vivid evidence, things that you read in the newspaper, over evidence that you don't even care about. You ignore new information, high probabilities to random events that happened just yesterday because they're fresh in your memory. You believe your own judgment. You see patterns in random data, like many people see patterns in stock movements, and they usually lose a lot of money. You take into account sunk costs, even though you shouldn't. Whatever you spent yesterday is gone. You shouldn't, but many people say, oh, I already spent $10,000. Why don't I go with this decision anyway? Well, you shouldn't. And you fail to ignore irrelevant alternatives. So I haven't even mentioned Kahneman and Tversky yet. I'm sorry. Danny Kahneman and Amos Tversky, Kahneman got the Nobel Prize in economics. They are two psychologists. two Israeli psychologists, also first-class mathematicians, but they're psychologists. So what they found is people rely on a limited number of rules of thumb, which reduce the complex tasks of assessing probabilities, etc., to just form a simple to come to a decision. And in general, these heuristics, rules of thumb, are quite useful, but sometimes they lead to severe and systematic errors. And what's important is that they are systematic. We all do the same errors. So they researched that and found out that the errors were quite systematic. And Kahneman got the Nobel Prize in 2002 for having integrated insights from psychological research to decision-making. Amos Tversky died very young at age 57, so he did not get the Nobel Prize. Let me give you an example. Linda, how one makes wrong decisions. Linda is 31 years old, single, outspoken, very bright. She majored in philosophy. As a student, she was concerned with issues of discrimination and social justice, and also participating in anti-nuclear demonstrations. Which is more probable? Linda is a bank teller. Linda is a bank teller and is active in the feminist movement. Now, Kahneman and Tversky asked this question to many, they did an experiment, and it turned out many people said Linda is a bank teller and is active in the feminist movement. And that's the wrong answer, because it is more probable that Linda is a bank teller and she may also be active in the feminist movement. That includes Linda is a bank teller, includes the set of women who are also active in the feminist movement. Nevertheless, many people opt for the second solution, teller and feminist movement. So sometimes a description may just lead you astray. Or let's say at the flea market, you see a set of 12 plates, 2 of which are cracked. People, when people were asked, they were willing to pay $7.20 for that. That's another experiment that Kahneman and Tversky did. And then they were asked, or other people were asked, for 8 perfect plates, but the same plates, but just 8, and they weren't cracked. And the estimated value was $8. Now, the 2 cracked plates should simply be ignored, but often they aren't. The set of 12 plates, 2 of which are cracked, you got 10 plates which were not cracked. Nevertheless, you were willing to pay only $7.20. Why? Because people automatically average out. For good plates, they're willing to pay $1 on average. For plates, some of which are cracked, they were willing to pay only 60 cents on average. So that's another irrational decision, but that's how people systematically make decisions. Or how do you ask a question? You probably heard this already. Imagine an outbreak of a disease, very pertinent now with Pfizer and all the other vaccines. It's expected to kill 600 people. There are 2 options. Vaccination A, 200 people will be saved. Vaccination B, 2/3 probability, nobody will be saved. 1/3, everybody will be saved. Most people opt for vaccination A, prefer A over B. Or you frame it differently, the same numbers, but you say 400 people will die. Or vaccination B prime, 1/3 probability that nobody will die, and 2/3 that 600 will die. Well, the majority of people that Kahneman and Tversky asked, they opted for B prime over A. So framing, how you ask a question, may make the difference in your decisions. Availability, whatever you know, may lead you astray. Many people think, unfortunately, vaccination of children leads to autism. What happened? Well, infants are vaccinated at 2. Autism first makes itself known at about age 2. So naive parents confuse coincidence with evidence. Or if you ask people, are there more deaths of lung cancer or traffic accidents? Many people say traffic accidents because that's in the newspapers. If somebody dies of lung cancer, it's not in the newspaper. But actually, I don't have the numbers, but many more people die of lung cancer than of traffic accidents. Fear of flying is another example. Flying is the safest way mode of transportation, but every air accident is hugely reported on in newspapers. And that's why many people are afraid of flying, even though it's much safer than driving a car. And nobody is afraid of driving in a car. So these are biases, and they're systematic and predictable. We are boundedly rational in a systematic and predictable way. We had the Linda example, the bank teller, availability, whatever information you have, adjustment from an anchor. That's, for example, if you go to a restaurant and you look at the wine list, and all the wines are very expensive, but there's one wine which is even more expensive. They never sell it, but they put it on the menu just so you think the other wines are a steal, and you end up buying a wine that's more expensive that you meant to buy because you compare it with an anchor. Sunk cost, many people take sunk cost into consideration, regression to the mean. Okay, these are all biases which are systematic. So Kahneman and Tversky, here they are, they discovered prospect theory. Prospect theory is how people actually make decisions. And it comes in 2 stages. When you're faced with a decision, you first edit the text, or in your mind, how to make the decision, and then you evaluate it. So editing it's basically editing. You combine things, you separate things, you cancel things that you don't want to consider, you simplify, you look at some options dominate all the other options, so you just go with that one. So that's editing, that's more or less textual editing. Now comes the evaluation, and comes in 2 parts. First, there's a value function. Previously, we had wealth and utility of wealth. And the second thing is decision weights. Previously, we used probability. And Kahneman and Tversky say, no, utility, that's not quite it. We need something else, which I'll describe in a moment. We need a value function, we need value. And probability, now people also don't really follow the rules of probability. They use decision weights. So the value function is the following. That's what we had with Bernoulli. We had this sloped, upward going, but sloped downward, diminishing marginal utility. And Kahneman and Tversky said, well, it's not quite like that. It's for gains. First of all, people look at changes in wealth. They don't look at absolute wealth. So you put the current wealth at the origin, and now you look at the gains. In the gains, you're actually risk averse. And for losses, they found out that people usually prefer to take risk when you're in the domain of losses. And also they say losses make you more unhappy than gains. So they say gains is sort of sloped this way, losses are more steep here. So that's the value function. And the other thing is the decision weights. They say they came up with 5 rules that people use, which are incorrect according to probability theory and game theory. Subcertainty probabilities don't add up to 100. These are technical, I wouldn't call them axioms, but technical rules that people use for decision weights instead of probabilities. And probabilities near 0 and near 100 are not defined. One doesn't really know what to do with such 0.001% of getting $1 million. It's either ignored, it's like 0%, or you don't really know what to do with it. So prospect theory, first you edit, and then you compute and maximize expected value using the value function to translate dollars amount into value, and you use decision weights to translate the probabilities. And I'm actually a few minutes before the end, but anyway, that's the book on which the whole talk was based. And if you want to purchase it, apparently you get 30% discount at Columbia University Press. And before I finish, I just want to tell you about my new project, Paradoxes. And you can see some of the paradoxes on my website, and I'd be very grateful for corrections and comments, because I'm not an authority on any of these, so I'll be happy to hear from you. Doron, I am, should I stop sharing? Yeah, okay. If there are any questions, I'll be happy to hear.
So, Dr. Z, it seems like we can't hear you again. But everyone, please thank George for this wonderful talk. Nice Zoom round of applause. Are there any questions for George?
Okay, I'm also happy. Okay, so let's call it a day. And
just one question. With Linda as a bank teller, and Linda's a bank teller and a feminist, isn't it true in a way, and you know I'm not a mathematician, that an unconstrained set is more likely to be true than any qualification on that unconstrained?
That's exactly it. That's why one should always go for Linda is a bank teller. But many people get hung up on the description, and just because this description is there, they actually come to the wrong decision.
So maybe they're interpreting it differently.
Okay, the question, I mean, Kahneman and Tversky were always very careful how they phrased everything. So it's usually their questions were not open to different interpretations. But of course, that could also be. But yeah, they were quite careful about that.
Yeah, I mean, someone just looking at that question could interpret it, the first choice, as a bank teller and a non-feminist, just because that's left out and the other one includes being a feminist. So I think a mathematician would not make that interpretation, but a layman might.
Yes, okay. I mean, when you read Kahneman and Tversky, it's all very interesting because you can have your own interpretation. And then when you continue with their paper, you realize, they already thought about that. But yes, of course, there are many things. It's not as clear-cut as the Maurice Allais things with the 89% and 90%. There it was clear mathematically that you're wrong when you change the your preferences. So Kahneman and Tversky, it's all much more framing. Also, it's sometimes very difficult and subtle, but anyway, they thought very carefully about all these things, and yeah. Anyway, but one can have one's criticism with their experiments.
Is there a next chapter to decision making to do with data? because we've never had so much data?
Yeah, that's computer science. I mean, that's when computers enter. Of course, lots of data, and artificial intelligence. I mean, maybe now with artificial intelligence, all this prospect theory and so on will be passé in a few years because everybody will have his artificial intelligence handheld device and make the correct decisions according to game theory. But right now we're still at where people make decisions in their head with all the biases, and we can actually tell the predict the biases. And the previous to last Nobel Prize, Richard Thaler, he's a behavioral economist, finance, and he has a fund, an investment fund, where he makes use of the biases that people have, and they undervalue or overvalue certain shares. He computes the true value and knows that many people will undervalue it or overvalue it for some reason or another. And I don't know how successful his fund is, but anyway, he does make use of all these biases.
So, George, so if I look at the Ellsberg paradox, it requires a mathematician, in effect, to find the equivalent cases that D prime and C prime are equivalent, whereas in most cases, nobody would have, or very few would have gone from one case to the other and says, oh, they are equivalent.
Which case do you mean? Well,
The 89% and the 80%, the 89%.
No.
Quite.
Let me tell you, Maurice Allais, there was a famous conference in Paris to which all the important people came. I mean, Milton Friedman, all these who had invented game theory. Oops, sorry. That was me to show that it's the end of the talk. So he had all the people whose pictures I showed you, Milton Friedman and the others. And they all fell into, not all, but many fell into the trap. And it was for them a real eye-opener that even though they are mathematicians and they are economists, and it's described in a paper how that Allais wrote that he asked them over lunch sometime. He made the experiment, but he also asked these people over lunch. And many of them just fell into the trap. And when he pointed it out to them, they were devastated because they had put all their career into game theory, and they realized it's a nice theory and it gives the optimal decisions, but people don't behave like that. So yeah, even mathematicians fell into the trap.
Yeah, that's what I said. That's very difficult to find that those are equivalent cases.
Yeah.
I see that at, your timer went off. It looks like the clock behind you, George, reads almost 1 in-the-morning. Do we want to take maybe one more question before we wrap up?
Yes, I was going to come in my pajamas, but I thought maybe I should be dressed.
Those aren't your pajamas?
Okay. Another question? Okay, I'll be happy to go to sleep. Thank you very much for being here.
Everyone, please thank George
Very
again.
good, very nice.
Thank you. Bye-bye.
Thanks, George. Bye-bye.
Bye.
Goodbye, everyone. See you back here next week.
Bye.